Today we are going to explain a new lesson, Capacitance and Dielectrics, which is chapter 26 in survey book. Anyway, from its title, it appears that we are going to talk about capacitors. So I guess you are all familiar with capacitors. It's not a hard topic, it's an easy topic, and it is okay. So definition of capacitors. What are capacitors? Usually, a capacitor is formed of two conductors placed facing each other. Between these two conductors, we have an insulator or a dielectric. So these two conductors can have any shape. They can be regular, they can be parallel plates, they can be irregular, they can be spherical, they can be cylindrical. We don't care. Any two conductors facing each other, and there's an insulator in between them, so we form a capacitor. What is the job of a capacitor? The job of the capacitor is to accumulate electric charge, is to store electric energy. One common type of capacitors is the parallel plate capacitor. You know all what is a parallel plate capacitor. If the capacitor is formed of two parallel plates, and these two parallel plates are facing each other in this way, such that they are separated by a distance d. So we say that we have a parallel plate capacitor. So this is just one form, but it's not. They must not be formed in this way. They can be formed in any shape. Okay, regarding that there is an insulator in between. So this is for the capacitors, the definition of capacitors. Let's take a look on how the capacitor works. If we connect the armatures of a capacitor to the poles of a generator battery, we have an accumulation of electric charges on the armatures A and on B. So let's take a look on the figure to the right. You can see that we connect our capacitor. This is a parallel plate capacitor. You can see that we have two conductors here. So these are conductors. And in between here, we have an insulator. It can be vacuum, it can be air, it can be anything. Okay, we have our generator. And you all know that when electrons leave the generator, electrons will leave from the negative pole of the dry cell or the battery. So electrons will move like this. So electrons will start moving. Okay, they will arrive to the armature B. So remember that we call the plates of the conductor, we call them armatures. تعول البطارية we call them poles. بينما الcapacitor we call them armatures. Anyway, when an electron arrives to the armature B or to armature B, it will stop there or it will accumulate there because in between A and B there's an insulator. It can no more proceed. So بيجي بيوصل الإلكترون بصير في عندي هون minus. This electron will repel an electron from armature A. So electron مقابله from armature A will leave its place. Okay, so an electron will leave from armature A. So there's an accumulation of minus here. And because an electron will leave armature A, we will get a plus on armature A. So there's a minus here and a one electron will arrive on B. An electron will leave from armature A. That negative charges will accumulate on armature B and positive charges will accumulate on armature A. So the electron will complete the circuit and okay, a current will flow on the circuit. Anyway, you can see that the number of negative charges accumulating on armature B is equal to the number of positive charges accumulating on A. So راح يكون عندي minus, minus, minus. Okay, so the same number will be accumulating on armature A, same magnitude, opposite direction, or opposite, senses of charges. Second notation that for a capacitor, the armature that is connected to the negative pole of the dry cell will be negative, and the armature that is connected to the positive pole of the dry cell is positive. So لاحظوا البلس على البلس والماينس على الماينس. And this is the reason why this happens. Okay, so you can see that the job or the main functioning of a capacitor is to accumulate electric charge on its armatures. And in this way, it is accumulating electric energy. They have done experiments. They have tried to understand more a capacitor. They have seen that if we vary the generator or the battery you are using, and each time we try to measure the quantity of charge Q accumulating on its plates. Okay, so you know that the capacitor will remain charging till its voltage is equal to the voltage of the dry cell. You all know this information. Each time we replace our battery with a different battery, the capacitor will charge to a new voltage. And if it charges to a new voltage, it will carry a new amount of Q, of a charge Q. Okay? They found out that the quantity of charge Q and the voltage carried by the capacitor are always proportional. And they called this proportionality constant the capacitance. يعني I will repeat them again in a different way. إذا نحن جينا وحطينا بطارية، كل مرة الكاباسيتر بيشرج على قد البطارية ورح يحمل كيو حسب الفولتج اللي هو بحامله. بغير البطارية أنا بتغير الكيو وعندي في جديدة، بغير البطارية كيو جديدة وفي جديدة. So الكاباسيتر إذا أنا بغيره بحطه بسيركوت مختلفة، التشارج تاعته بتتغير والفولتج كمان بيتغير. بس شو ما بيتغير؟ الكاباسيتنس تاعته. The capacitance is a characteristic of the capacitor. The capacitance does not change. It remains always constant. Similar to resistance of a resistor, the resistance does not change. If I place a resistor in a circuit, بيتغير الفولتج والcurrent اللي مرئين بالresistor, but the resistance does not change. It's as if it is the name of the resistor or the name of the capacitor. So the capacitance is a characteristic of the capacitor. It always remains constant. What changes? The voltage changes according to the circuit, the combination of the circuit, and the charge carried in the capacitor كمان varies with the voltage. But C is a characteristic. What is a characteristic? It depends on the design of the capacitor. How much are the plates? How much large are the plates? The distance between them, okay, etc. It depends on the medium in between, the dielectric in between the plates. So it depends on the fabrication of the capacitor and nothing more than that. Okay, you all know that capacitance C is measured in farad. Farad is a large unit, so you will mainly see that we use millifarad, microfarad, nanofarad, because farad is a large capacitance in reality. Okay, so بالعربي capacitance هي الساعة، هي قد ايه بساعة. كل ما كان C أكبر كل ما كان عنده capacitance أعلى. Okay, so this is in general for a capacitor. I'm writing here that remember that QA is positive, QB is negative, and QA it's equal to minus QB. يعني by convention when we say مثلا find the charge of the capacitor, find the charge of the capacitor, we mean the positive plate. يعني نحن بيكون قصدنا charge of the capacitor الQ، نحن مسمينها هون Q. We mean by it which is QA. So no need to just find say QA في عنا plus وفي عنا minus. We just say we have only one positive charge and we know directly that there's another negative charge on the other plate, same magnitude, opposite sign. So that's it. So بس نسألك عن charge of a capacitor, we mean by the charge of the positive plate by convention. Okay, one more thing, remember that VAB, the voltage, VAB is positive, while VBA is negative for a capacitor. Once you move from positive plate to a negative plate, you are measuring a positive voltage. Once you move from the negative plate to the positive plate of the capacitor, you are measuring a negative voltage, similar to a dry cell. Okay, this is for a capacitor. In general overview on a capacitor. As I have said, that the capacitance of the capacitor depends on the characteristics of the capacitor. Let's see if this is true. We are going to calculate the capacitance in 3 different cases. And for a parallel plate capacitor, this is the first one. For a cylindrical capacitor and for a spherical capacitor. This capacitance is only an application on Gauss's law and the thing and calculating the potential. Yani on the chapters 25 and 24, the chapters that we have already studied. So consider them as examples, as if we are solving just exercises. Okay, there will be just one more exercises for you to solve. We are going to find the capacitance of a parallel plate capacitor. This parallel plate capacitor is formed of two, as you can see, two parallel plates separated by a distance d. What do we have to find? We have to find C. What is C? C is the capacitance. Anyway, as you can see, this plate A carries charge Q. Plate B is carrying a charge minus Q. Okay, this is the given. What do we have to find? We have to find C, the capacitance of such a capacitor. So by definition, C, it's equal to Q over the voltage of the capacitor. We have explained this in the previous slide. So C is simply Q over VAB. So if we are able to calculate this, so we can find C. For a parallel plate capacitor, we have found that VAB, it's equal to E times D, where E is the electric field in between the parallel plates, and D is the distance in between them. And this formula also, I've explained it or appeared in previous slides. So E equals VAB over D, which means VAB equals E times D. Okay, for a parallel plate capacitor. From previous chapters, we have shown that E equals sigma over 2 epsilon 0 for one plate. And for two plates, if I apply Gauss law, I find the electric field for one plate, it's sigma over 2 epsilon 0. Then for two plates, electric field will be directed from the positive plate to the negative plate like this. So I will get E1, I've explained this before. So I will get E1, which is equal to sigma over epsilon 0I, and E2 will, this is EA coming from the positive plate and EB coming from the negative plate. Both of them are directed to the right, so I will get EA equals sigma over 2 epsilon 0I, and I will get EB. EB is directed towards the negative plate. EA is directed away from the negative plate. It's also sigma over 2 epsilon 0. Come on, I've explained this in a certain exercise. If I add them, because they are both directed in the same direction, no need to project, both of them are along I direction. So E total in between the plates will be sigma over 2 epsilon 0. So we will get E equals sigma over epsilon 0 I. We add them. Okay, so we will get the electric field in between the two plates, sigma over epsilon 0. Now we find E. We will substitute E up. So E is substituted by sigma over epsilon 0 D. Just arrange, I brought epsilon 0 up. Okay, I replaced sigma Q by sigma S because sigma is the surface charge density for plate A and plate B. They have the same sigma. Okay, so we will same sigma, but one of them is plus and one of them is minus. Same magnitude of sigma. We can say that. So Q equals sigma S. Anyway, sigma with sigma, they are cancelled. We will get epsilon 0 S over D. So we will get C equals epsilon 0 S over D. So as you can see, the capacitance depends on epsilon 0, which is the electric permittivity of vacuum or air. S, it is the surface, it's the surface of the plate surface. A and B, they have the same surface in my case here. And D is the distance in between. So you can see that C, the capacitance, depends on the characteristics of the shape of the capacitor, the fabrication of the capacitor. And this is for the first one. Okay. Now, if the dielectric in between the plates A and B is not vacuum, so the derivation will be the same, except that we will replace epsilon 0 with epsilon, where epsilon is the electric permittivity of the medium. So each medium has its own epsilon. And if we are talking about air, water, oil, etc., each medium has its own epsilon. Why? Because كل ميديوم بينقل الالكتريك فيلد بطريقه مختلفه. فاذا انا بالنص عندي فاكيوم مش مثل اذا في ماده ثانيه. اوكي الالكتريك فيلد جوا رح ينتقل بطريقه مختلفه. فالالكتريك فيلد فرح يبين هيدا عندي وين بالابسلون. Anyway, so sometimes instead of giving you the electric permittivity of the medium, we define something called relative permittivity, which is epsilon r. I'm talking about epsilon r, which is equal to epsilon over epsilon 0. Now we know that each medium has its own epsilon. والvacuum اسمها epsilon 0. But sometimes instead of, because the numbers are not beautiful numbers, okay, we define something called relative permittivity, which will give us a smaller number, okay? And what is relative permittivity? It's the relativity with respect to the relativity of vacuum. يعني epsilon على epsilon 0. So if you know epsilon r, you can find epsilon. Simply epsilon is epsilon r, epsilon 0. So either you are given epsilon for the medium or epsilon r of the medium. بكل الأحوال فيك تجيب الابسلون انت. يعني بتكون given الابسلون. Okay, got it. أو you've got epsilon r, you can calculate epsilon. That's it. If you remember, أكيد أخذين شي مرة من المرات something called relative density, which is the density of something with respect to water. نقسم الدنسيتي تاعته على الدنسيتي للمي. This is called relative density. بيطلع مثلا أنا عندي for example الأويل عنده density 900 والمي 1000. نقسم 900 over 1000 يطلع عندي 0.9. This is called relative density. يعني density نسبية. Okay? But anyway, if you know the relative density, you can find the density. You multiply by the density of water with respect to something. It's just relative to something. And this is the relative permittivity. It's just a number. Okay, in order to define the permittivity of a certain medium. هلا by experiments, this epsilon r is usually greater than 1. كقيمة هي أكبر من 1. So كل الميديا التانيين الغير الفاكيوم عندهم epsilon أكبر من الابسلون 0. Which means that if I replace vacuum by any other insulator راح يكون عندي الكاباسيتنس أعلى. يعني بكل الأحوال إذا أنا الأبسلون أكبر من أبسلون 0 because epsilon r is greater than 1, so I will get C greater than C0 إذا أنا اعتبرت C0 إذا أنا حاطة in between vacuum C إذا أنا حاطة any other material in between my plates. Okay, so this is the difference between them. I'm saying that C, what is C? C is the capacitance with dielectric in between. Dielectric عنده epsilon. هون C0 هي الكاباسيتنس with dielectric هو vacuum or air vacuum. Okay, epsilon 0. So you can see that C equals epsilon r at C0 and epsilon r is greater than 1. So it's obvious that C is greater than C0. So a capacitor with a material other than vacuum has a larger capacitance. It has a larger capacitance. So this is the way we increase the capacitance of the capacitor. We choose a material that has a higher relative permittivity or permittivity. Okay, so the last sentences talks about C. As you can have seen, that C depends on the shape of the armatures, surface of the armatures, distance between them, and the nature of the dielectric between these two armatures. And this is for this parallel plate capacitor. Now let's move to the second case, which is the cylindrical capacitor. The cylindrical, let's consider a cylindrical capacitor. We have a cylinder inside, it's carrying a charge plus Q, and the one outside is carrying a charge minus Q. Okay, what do we have also? Okay, so this is, they are two conductors, as you can see, two conductors. برا shell وجوا عندي. Okay, it has a radius R1, the outer one has a radius R2. And let's consider that our capacitor has a length L. Okay, it has a length L. What do we have? We have to find the capacitance. To find the capacitance, we have to say that C, we will get C equals Q over V. So we have to calculate V. نحن لازم نقسم ال V. Remember that Q هي التشارج اللي على positive plate. نحن هلا من شوي قلناها. وال VAB, it is the integral from the positive plate to the negative plate. So to solve this, I will take A here. أنا بجيب ال voltage between the two plates will be على البرانية. So this is B. Okay, so this is VAB. I will calculate VAB. To be able to calculate VAB, with voltage between the two plates, I have to apply Gauss law. رح نطبق Gauss law. I will solve it here. Anyway, I've written just the answer in the okay, using Gauss law, Q equals 2 over 2 pi RL epsilon 0. But I will solve it anyway. So we choose this cylindrical Gaussian surface, which is dotted. As you can see, it's dotted in yellow. And I'll apply, so integral EDA, it's equal to Q inside over epsilon 0. You all know this information that E has 3 sides, and the lateral side is the only one that does not sum up to 0. The sides, the two disks to the left and to the right will sum up to 0, so no need to consider them. We will get E times 2 pi R. I won't call, okay, L. أنا أخلي Gaussian surface على قده. It's okay. You can do that. You can do that. It's not wrong. You can choose any Gaussian surface. Equals Q inside. What is Q inside? It's كلها Q كلها. So it's Q over epsilon 0. So we will get E equals Q over 2 pi RL epsilon 0. And this is E. So this is found where? It's found here. So this is it. This is E. So this is E, we found E. Now what do we have to do? Just do the integral. Integral from A to B minus integral from, sorry, VA minus VB equals minus integral from B to A EDR. So we replace E with its value. We replaced E with its value. We have everything constant except R. So R is our variable. R is the variable. So I've flipped the integral because of the minus. You can keep it, just substitute, it's okay. And you know that A is found at a radius 1, R1 will be, and the radius, this is the radius R2, and this has the radius R1. So just integral dr over R will be ln R. So substitute R1, R2, and R1, you will get ln R2 over R1. And this is VAB. So now I have to calculate C, divide Q by VAB. It will be like this, Q will be cancelled. And we will get C equals 2 pi epsilon 0 L over ln R2 over R. Again, the capacitance of a cylindrical capacitor depends on the medium in between, the length of the capacitor, and the resistances. Sorry, the radii. Okay, I was saying something else. And the radii, R1 and R2. The capacitance does not depend on the voltage. It only depends on the fabrication of the capacitor, on the shape of the capacitor. Okay, so that's why it's a characteristic. Now let's move to the third one, which is the spherical capacitor. Again, here we have to, let's choose A here and let's choose B here. And we have to calculate VA minus VB or VAB, which is VA minus VB, which is equal to minus integral from B to A EDR. كلكم تعرفوا you choose Gaussian surface هيطلع معكم KQ over R square بحالة circular, so it's minus integral KQ over R square dr from B to A. So I've placed this here. Okay, so هيدي ال E هي KQ over R square. You can find it using Gauss law. It's the same as I have already solved. And this is the integral. So this is a constant. It goes outside. Integral 1 over R squared is minus 1 over R, and there is minus outside, so I will get 1 over R. Substitute A and B, I will get, remember that A is inside, which had a radius R1, and B is outside, which has a radius R2, so I will get 1 over R1 minus 1 over R2. Some calculation, I will get this last form. Now let's find C, divide Q by VAB, we will get this form, and we can see that it depends on R1, R2, and epsilon. The type of dielectric, first radius, second radius. And this is the capacitance and how to calculate it for certain shapes, for certain, خلينا نقول symmetrical shapes. Now let's move to something more important, which we use too much in our questions, grouping of capacitors.
دكتور
What?
السلايدز اللي كنتي عم تحكي عنهم هلا هديك السنة الماضية كانوا cancelled.
Yes, they were cancelled. Anyway, هن ما في they have يعني ال V it's not cancelled and E is not cancelled. You can consider them as just examples.
أنا قصدي إنه لأنه ما حنشتغل على الكاباسيتر على إنه هودي الروز أنت هلا عم تعملينهم derivation ما هيك؟
You can consider them just as an examples to solve. يعني إذا أنا طلبت منك تجيبي ال V بهيك حالة ما بتعرفي تجيبيها؟
بلا.
Okay, that's it.
أوكي دكتور.
بس هالقد بثلاث حالات مفترض تعرفي تجيبي ال V بثلاث حالات. بتجيبي ال E وتجيبي ال V. So it's just for you to practice. هلا نحن كسي مش مطلوب مننا I guess هلا احنا ما حكينا بس I guess this year it's also not required to find just C يعني ما في question find C for a parallel plate capacitor or find C for a cylindrical capacitor, but you should know how to solve this. Okay, now for parallel grouping. Let's go to parallel grouping. Parallel grouping, how to like what? The main problem for students in first year is to distinguish between capacitors in series and capacitors in parallel. This chapter is very easy, but the main problem for students, I don't know why, is to distinguish between capacitors in series and capacitors in parallel. This is the main job. Once you distinguish correctly, you can write your answer correctly. If you distinguish them wrong, then your answer will be directly wrong. Okay? When I solve, I will give you hints how to find them. Okay? So there's a certain way how to consider things that consider capacitor series and how to consider them parallel. Okay? And for sure, your answer will depend on the correct choice of series and parallel capacitors. There's كمان something أنا ملاحظة إنه هو بالنسبة للتلاميذ بيعتبروه بديهي. ما ضروري يكونوا اثنين يا series يا parallel. They can be لا series ولا parallel. It depends on the circuit. How to know if they are, for example, series? Same current passes through them. Same current. Okay, passes through them. They are considered series. How to know if they are in parallel? They must have the same voltage. That means they are only connected by wires from both sides. Anyway, when I solve, we will encounter difficult circuits, not the simple circuits like this one, but this one I will explain it. But just to derive the formula, you will see that once you get the idea, you can figure out if they are series or parallel. Okay. What is an equivalent capacitor? First of all, an equivalent capacitor is a capacitor that replaces other capacitors and it carries the same amount of charge as all of the capacitors. It carries the same quantity of energy. It carries the same quantity of energy, not only the, not the charge, I mean the energy, the same quantity of energy as the other capacitors. So إذا الأول حامل energy على قد، الثاني energy على قد، الثالث energy على قد، the equivalent will carry the same amount of energy as all the capacitors. So let's take in our case, let's start with parallel grouping. I have 3 capacitors, C1, C2, C3. You can see that the plus is connected to plus، يعني هيدي Q1 هون، Q2, Q3 كلهم مع البلس، والماينس مع جهة الماينس, so it's okay. Now you know that I want to replace my capacitors C1, C2, and C3 with only one capacitor called C equivalent carrying Q equivalent. What is my job is to find Q equivalent and the C equivalent. Anyway, I have to find C equivalent, the capacitor that does the job in replacing the 3 other capacitors. This is C equivalent. Okay, let's think about the charge. The charge accumulates on the capacitor because of the current. يعني لما الكرنت يمشي هو اللي بيحمل معه التشارج بيوصلنا على the capacitors. So you can see that when the current moves, here the current will divide to 3 portions such that the sum of I1 plus I2 plus I3 is equal to I main. So this is I1, let's call this I1, this is I2, and this is I3, and this is I main, which is the main current coming from the dry cell. So this is I main here. So it appears that I main, it equals to I1 plus I2 plus I3 according to the law of addition of currents, or the junction rule. So منطقيا لازم يكون عندي Q equivalent, which is the charge accumulated on C equivalent, it's equal to Q1 plus Q2 plus Q3. Remember, تعريف الكرنت charge per second. يعني الكرنت is a charge هو بالحقيقة هو dQ over dt. It's the variation of charge per unit time. So I is related to the charge crossing or flowing per unit time. So if I main is equal to I1 plus I2 plus I3, so I will get Q equivalent must be equal to Q1 plus Q2 plus Q3. So this is the first equation. Now let's replace Q equivalent. You know Q equals CU or CV. So Q equivalent equals C equivalent times VAB, which is the voltage VAB, and Q1 equals C1 V1, Q2 equals C2 V2, and Q3 equals C3 V3. Now, because the 3 capacitors are in parallel, then VAB is equal to V1, it's equal to V2, it's equal to V3. So I can divide here by V1, V2, V3. It's the same V, divide by V. I will get C equivalent equals C1 plus C2 plus C3. This is the first result. So if they are connected in parallel, C equivalent is the addition of the individual capacitances. We add them. We add them one by one. Okay? So if we have n capacitors, we just add simply the capacitances, C1 plus C2 plus C3, we just add them. So general formula, C equivalent equals sum of Ci. If they are all equal, so it will be, if they are all equal to C, simply they are NC. So C plus C plus C plus C n times, it is NC. So this is if we are talking about capacitors in parallel. When we solve, remember something. نحن عم نحل capacitors in parallel لازم نخلي براسنا شغلة مهمة. Capacitors in parallel, they have equal voltage. والcharges تاعولن they are added. يعني V1 equals V2 equals V3 equals V equivalent. ال V equivalent كلهم. Q equivalent equals Q1 plus Q2 plus Q3. So these relations help us to solve this one, 1 and 2. They help us to solve. In addition to the relation of C equivalent هي مجموعة C. So we use these 3 equations, not only C equivalent equals C1 plus C2 plus C3. Sometimes we need to know that Q equivalent equals Q1 plus Q2 plus Q3, and the V's are equal. So we have to keep in mind these three relations. We may need them. Okay, so usually I stick to saying that if we have parallel grouping, then voltages are equal. When you know voltages, you can know Q. يعني أنت معك ال V بتجيب لي Q equals CV. So once you use one equation, you can directly get the other. But anyone, you can use also one, which means Q equivalent is the sum of Q's in the circuit. Okay. So this is for parallel grouping. Now let's talk about series grouping. In series grouping, you can see three capacitors. They are connected in series. Same current passes through them. So if same current passes through them, this is I main passes through them. So this is I. The same I that passes through the first one passes through the second one, passes through the third one. So I, which is the current, it is the one that carries the charge. So if a charge arrives to the first one, the same charge will arrive to the second, the same charge will arrive to the third, because the current is the one that carries the charge. Okay, so this is I down. So you can see that also Q equivalent has the same charge as Q1 Q2 و Q3. I will remind you انه نحن ما بنحكي عن الماينس، يعني بنعرف في بلس وفي ماينس، بس لما نقول charge of a capacitor we mean the positive plate. Okay, so Q equivalent, you can see that Q equivalent is equal to Q1, it's equal to Q2, it's equal to Q3. So this is the first information that you have to remember in series grouping. Series grouping, Q's are equal. Parallel grouping, V's are equal. Voltages are equal. Here, Q's are equal. Q equivalent equals Q1 plus equals Q2 equals Q3. Okay? From the law of addition of voltage, you will see that VAB is simply V1 plus V2 plus V3. So substitute VAB with Q over C equivalent. Anyone, it's Q equivalent over C equivalent. V1, it's Q1 over C1. V2, it's Q2 over C2. And V3, it's Q3 over C3. But we've got Q equivalent, Q1, Q2, and Q3 equal. Let's divide by Q. So we will get 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. So you can see that grouping of capacitors in series is similar to grouping of resistors in parallel, and grouping of resistors in in series is similar to grouping of يعني they are different. Okay, يعني بعكس بعض. Anyway, so if we have n capacitors connected in series, simply we have to do 1 over C1 plus 1 over C2 plus 1 over C3, and at last we have to find C equivalent. يعني بالاخر نحن بنرجع بنقلب الجواب كما يطلع معنا C equivalent، نعمل inverse تاعله. Okay, and if they are all equal, so I will get 1 over C plus 1 over C plus 1 over C plus 1 over C, and times I will get N over C, and C equivalent will be C over N. That means grouping of capacitors in parallel will decrease the capacitance. لأنه إذا أنا عندي capacitor واحد بيكون C، 2 capacitors in parallel identical بصير عندي C على 2. So I will get a lower capacitance for the equivalent capacitor. Okay؟ لما أنا بحطهم in parallel بكون عم زيد الكاباسيتنس، بس لما بعلقهم in series بكون عم خفف الكاباسيتنس تاعتهم. اوكي، يعني ك equivalent بكون الكاباسيتنس total عم تصغر. It's better to connect them in parallel to increase the capacitance of the capacitor. So again, what do we have to remember? كمان you know that if we have only two capacitors, C equivalent is simply C1 times C2 على C1 plus C2. I guess I've written it somewhere. Okay, if not, it's not written here. Okay, if we have only two capacitors, no need to use this 1 over C equivalent equals 1 على C1 plus 1 على C2 plus 1 على C3. You can just use 1 over C equivalent equals 1 over C1 plus 1 over C2. We will get 1 over C equivalent equals C1 plus C2 على C1 C2. So we will get C equivalent equals C1 C2 على C1 plus C2. So this is only used if we have two capacitors. More than two capacitors, no, you have to use the main formula, which is this one. Okay, what do we have to keep in mind? Parallel grouping, these are equal. We add them, and we add C's. Series grouping, Q's are equal, and 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. And this is for the capacitors. Some remarks which help us to solve some questions. Okay. Capacitors in series have same charge. So as I have said, series means same charge. V's بينجمعوا يعني V equivalent بتساوي V1 plus V2 plus V3. يعني هون أنا عندي Q equivalent equals Q1 equals Q2 equals Q3. With capacitors in parallel, we have same voltage. V equivalent equals V1 equals V2 equals V3. And if Q's are equal, هذا بيعني إنه V equivalent هي V1 plus V2 plus V3. وهون عندي Q equivalent, it's equal to Q1 plus Q2 plus Q3. I have to keep this in mind because this will help me solve problems. Okay, in addition to أنا أعرف C equivalent. Okay, what is the job of the capacitors? Its job is to store electric energy. Initially, when we place a capacitor in a circuit, if it is empty, it means that Q is 0 and V is 0. So you will encounter many problems, mainly from previous sessions. In the last sessions, we did not include this idea, but this idea will help you solve many questions. It's just a hint, a small hint, so don't worry. So at T0, because the voltage of the capacitor is still 0, يعني بعده ما شرج، بعده الفولتج تاعه صفر، يعني أول ما بده يشرج، I can consider the capacitor as a connecting wire. So if he's asking me to solve the circuit at T0, when the capacitor is still uncharged, I simply replace my capacitor by a wire and solve the whole problem. I don't see the capacitor, I consider it as a wire. So بس هيدي المعلومة. If at T0, capacitor empty, consider the capacitor as a wire and solve your problem. Ignore the capacitor. Okay, if T is infinity, after 5 tau, we all know that the capacitor is fully charged to a certain voltage. We don't know, it depends on the circuit. Okay, when the capacitor is fully charged, no more current crosses the capacitor. Okay, so in this case, the capacitor carries a voltage, عنده voltage, it has a voltage, but no current crosses the capacitor. So I can consider the capacitor as an open circuit. يعني أنا هونيك محل الكاباسيتور موجود كأنه circuit مفتوحة. في voltage بس ما في current. So I can consider I in the zone محل موجود بالبرانش الموجود فيه عند الكاباسيتور I to be 0 in that place. So these hints كمان we use them when we solve.
دكتور
What?
بليز بس فيك تعيدي آخر هنت قطش الصوت عندي لو سمحتي.
Okay. I've said that after waiting for a long time at T infinity or for يعني after 5 tau, you all know that the capacitor is fully charged. The capacitor is fully charged by a voltage that corresponds to the circuit depending on its position in the circuit. So بس يصير fully charged, it will carry a voltage, it will carry Q, رح يكون عنده charge, it carries a voltage, okay, but it will act as an open circuit, يعني no more current will cross on it, in it, no more current will cross. So I can consider that the branch containing the capacitor has zero current. يعني إذا هو موجود بشي branch, يعني وين ما كان يكون, let's consider just a circuit. So this is a resistor, this is a capacitor, this is another resistor. Let's consider, for example, here a resistor. This is a resistor. This is a, okay, this is a battery, for example, like this. After a very long time, the capacitor will charge. It depends on the circuit, but the capacitor will charge to a certain voltage and to a certain Q. Let's just ignore how much Q and V. Okay, but this is not our job in this lecture, but it will anyway, it will be fully charged and no more current will cross the circuit. هلا إذا أنا بطلع بالcircuit تاعتي, the current will come here like this. It will divide here to two parts. Portion that will move in the portion where the capacitor is found and the other in the resistor, صح؟ So أنا إذا كان الكاباسيتور fully charged بطل شيء يمرق بهيدا البرانش. خلاص هون ما عادش في current. كل هيدا البرانش ما في بقلبه current. Did you get the
Okay,
idea?
doctor, thank you.
That's the
شكرا.
idea. So the branch that contains the capacitor will have zero current. As if it is an open switch or open circuit. Okay. So energy stored in the capacitor. We have said that the capacitor was mainly designed to store energy. You have seen the first slide in the lecture. It has someone, this is called the defibrillator, I guess. It's used to do an electric shock for people having a heart attack. You all know that. So it's placed in a certain way in order to allow the electric current to pass through the heart and allow the heart to beat again. So this medical instrument, in reality, it uses a capacitor. So why it's placed in this lesson? It's just, I've just cropped the figure from the lesson from the book of survey, just to keep the same lesson, okay, not to change the lesson or the topic of the lesson. Anyway, so this machine or this medical instrument, it uses a large capacitor to store energy or to store electric energy. And when this electric energy is stored, بس إن يكبسوا على الزرين، في زرين عليها، بس يكبسوهم بينزلوا دفعة واحدة اوكي بالهيومن بودي وبيمرقوا من from one electrode to the other. بتمرق الكرنت من واحدة، يعني بيمرق مثلا من هون لهون current. So بيمرق بقلب الهارت. And if someone is having a heart attack or something, or the heart has stopped from working, so they can help the heart to rework again. Okay, so this is why this figure is placed at the beginning of the lecture. So just anyway, I was talking about that because the capacitor, the job of the capacitor is to charge energy, is to charge electric energy. Okay, so how to calculate the electric energy stored in the capacitor? So you have seen that dW, let me just read the second line. If dW is the work done to transfer charge dQ to plate of a charge Q, then dW is equal to V dQ. So we have seen that from the from the previous chapter, that the energy equals QV, يعني اليو كان بتساوي QV. So this is the energy in reality, it's QV. So if I'm searching for the infinitesimal work done to place a charge dQ on a plate having voltage V, so it will be simply dQ times V. احنا أخذنا electric energy هي voltage times Q times charge, the electric energy. So dW الwork أو energy, small energy, it's V dQ. We will replace V in a capacitor by Q over C dQ, and because we are looking for the total work done by a capacitor, we will do an integral to dW. We give it the symbol energy. Okay, we will get remember انه نحن بالدرس قبل كانت اليو عندنا QV, it's the same هون بس هنا عم نجيب DU, it's V dQ. Okay, so like this, it's the same. بكل الأحوال, let's integrate. We've replaced V by Q over C. We can replace V by dQ, something related to V. We can do that, but this method is easier. So the capacitor is being charged from 0 till big charge Q, and we will get half Q square over C. Anyway, Q رح تعطينا half Q square over 2 أو Q square over 2. So integral of Q صغيرة هي Q square over 2 وعندي 1 على C. And from 0 to Q, we will get half Q square over C. So this is the energy stored in the capacitor. So you all know that we can replace Q by CV. So if we replace Q by CV, we will get half CV squared. And we can replace C by Q over V. By C, it's by Q over V. And we will get half QV. So we have three formulas for the energy. You can call it U, you can call it W, okay, as you like. I call it here, I've called it here U. So it's half Q squared over C equals half CV squared or equals half QV. بكل الأحوال, what is this potential energy? It gives me the energy stored in the capacitor at this instant بهاللحظة. So قد ايه عنده V قد ايه هلا عنده charge. Okay, and by the way, if I calculate the energy stored in the equivalent capacitor, it's equal to the energy, to the sum of the energies stored in each capacitor alone. If I add them all together, they will be equal to the energy of the equivalent capacitor. This is the definition of the equivalent capacitor. It is the one that carries an energy equal to the sum of individual energies of all capacitors. It does their work. Okay, so this is for this lesson. Does anyone has a question?
Doctor?
Yeah.
Are we responsible only for the green